We're diving straight into a quest that's, well, literally as big as the stars. The global push for clean energy and a technology that promises to deliver it by, mimicking the power of the sun fusion.
Exactly. Fusion power.
Today, we're zeroing in on the two main players, the frontrunners in magnetic confinement fusion, Tokamaks and Stellarators.
Yeah, these are really humanity's biggest bets right now for harnessing fusion and understanding how they work and maybe more importantly, how they're different.
Crucial, right?
It's going to be really crucial as we try to figure out this sustainable energy future.
Exactly. So think of this as like your quick guide to getting up to speed on these fusion reactors. We'll break down the basics of both designs, uncover some surprising twists in how they develop.
Yeah, there's quite a history there.
And explain why this Wendelstein 7X project in Germany has everyone in the fusion world talking.
Right. Our main source is a pretty detailed comparison of the two, the Tokamak and the Stellarator.
And we're aiming to pull out the key info about their history, their, core mechanics, and what the latest experiments are telling us.
Our goal here is really just to give you a clear picture of these cutting-edge reactor designs and the sort of ongoing debate about which one might hold the most promise for actual power plants down the road.
Right. We'll stick to the fundamental ideas and why they matter without hopefully getting too bogged down in the super technical jargon.
Okay, let's unpack this. Maybe start with the Tokamak. It's got that Russian name.
Ah, yes. Toroidalnaya camera is magnitnimi katushkami.
Which translates pretty directly, right? Toroidal chamber with magnetic coils.
It does. Gives you the basic picture. Donut shape.
That's the main structure. A donut-shaped vacuum chamber for holding the super hot plasma.
That's where the fusion happens, yeah.
Yeah.
But keeping something that hot contained,
Yeah.
that really comes down to a complex dance of magnetic fields.
Right. And there are three key ones in a tokamak, yeah. First, the toroidal field.
That comes from big coils wrapped around the donut, the long way.
Like the main squeeze, keeping the plasma going around the circle.
Exactly. That's the primary force stopping the plasma particles flying outwards. But that's not enough by itself.
Okay.
You also need the poloidal field.
And that one's generated differently, isn't it? By a current in the plasma itself?
Precisely. And that current isn't just there. It has to be induced.
Ah, the transformer effect. There's that big magnet in the hole of the donut.
Yeah.
The central solenoid.
Right. It acts like the primary coil of a transformer. The plasma ring basically becomes the secondary coil.
And current flows through it. Clever.
Very. And that plasma current is vital because it creates the poloidal field, which loops around the plasma the short way, sort of through the donut hole.
Got it. Toroidal field around the long way, poloidal field around the short way, and the third one.
The vertical field. That comes from other external coils, the poloidal field coils. Think of them as fine-tuning. They shape the plasma, position it just right inside the chamber.
Okay, so you've got the toroidal field, the poloidal field. They interact. And the result is this kind of spiraling helical field.
Exactly. That helical twist is the key to confinement.
Like twisting water from a hose. Keeps it together.
Sort of, yeah. It forces the charged particles, the ions and electrons in the plasma, to follow these spiral paths, keeps them away from the walls.
Okay, but here's the catch with tokamaks, right? They rely on that induced plasma current.
Induced by the changing magnetic field from the central solenoid.
So you can't just run it continuously like that. Because the solenoid current can't just increase forever. You need that change. Faraday's law.
That's the fundamental issue for steady-state operation.
Yeah.
Using induction alone. You get pulses, on, off, on, off.
Which isn't ideal for a power plant.
Not at all. That's why there's so much research into alternative ways to drive that current, using radio frequency waves, for instance.
Or that bootstrap current thing.
Or the bootstrap current, yeah, which is a current the plasma sort of generates itself under the right conditions, trying to get away from relying purely on induction.
Okay, that's the tokamak in, well, a nutshell. Now, let's pivot to the Stellarator. Cool name.
Stella for star, generator.
Jetta.
Generator star energy. It also has that donut shape, visually similar.
Right, toroidal, but the big difference is the magnetic field generation, yeah.
Huge difference. In a stellarator, the entire magnetic field needed to confine the plasma comes from external coils.
All external.
All external. And crucially, these coils aren't simple loops like in a tokamak. They're incredibly complex, twisted 3D shapes, non-axisymmetric.
So no need for that big central solenoid, no induced plasma current for the main field.
Exactly. That whole transformer mechanism is gone. The necessary twist in the magnetic field lines the rotational transform that gives stability. It's all achieved purely by the intricate geometry of these external coils. Their specific shapes are engineered to create that twist.
Wow. And the big advantage there is continuous operation, steady state.
That's the inherent promise.
Mm-hmm.
Because the magnetic field is generated by external coils carrying steady currents, there's no fundamental reason it has to pulse.
Which sounds perfect for a power grid. Constant power.
That's a major potential selling point for baseload power. Wendelstein 7X, for instance, is explicitly designed for long pulses. They're aiming for 30 minutes.
30 minutes. Compared to the typical pulsed tokamak, that's huge.
It's a massive step towards demonstrating continuous operation is possible.
But I'm looking at pictures of these Stellarator coils. They look unbelievably complicated, like an engineering nightmare.
Oh, they absolutely are. That's a core challenge. Designing them and then actually building them with the required precision. It's incredibly difficult.
Yeah, I bet.
And that complexity is a big reason why tokamaks became dominant for a long time. They seem simpler, engineering-wise.
But modern Stellarators have some tricks up their sleeve. You mentioned quasi-symmetry.
Right, that's a key design principle in machines like W7X. It's a way to optimize the complex 3D magnetic field shape to behave more like a simpler symmetric field in certain ways.
Okay.
This helps significantly improve plasma confinement and stability, tackling some of the historical weaknesses of Stellarator designs.
It's fascinating that both concepts came about around the same time, the 50s. Tokamak in the USSR, Stellarator in the US with Lyman Spitzer.
Yeah, Spitzer's Project Matterhorn at Princeton was actually the early leader. Lots of buzz around Stellarators initially.
So what happened? Why did tokamaks take over?
Well, in the 1960s, results started coming out of the Soviet Union, especially from the T3 tokamak. And they were surprisingly good. Much better plasma confinement, better stability than the Stellarators of that era were achieving.
Experimental results changing the game.
Absolutely. And then when British scientists went over, measured T3 themselves, and confirmed the results, that really shifted the global focus.
Everyone jumped on the tokamak bandwagon.
Pretty much. Big projects like JATE in Europe and eventually the International ITER project all followed the tokamak path.
But Stellarator research didn't completely die out.
No, it continued, albeit with less funding and focus. Researchers kept plugging away, trying to understand the physics better, improve the designs, figure out how to build those complex coils more effectively.
And now we're seeing this Stellarator renaissance. What sparked that?
A convergence of things, really. Firstly, huge advances in computing power. We can now model and optimize these incredibly complex 3D magnetic fields with amazing precision.
Using things like quasi-symmetry.
Exactly. And secondly, big improvements in manufacturing technology. Advanced winding techniques, even using things like additive manufacturing for some components, are making it actually possible to build these intricate coils to the needed tolerances.
So the tech caught up with the theory.
In many ways, yes. So Stellarators are now seen as a genuinely competitive alternative again. And Wendelstein 7X is really the flagship experiment designed to prove that potential.
Okay, let's quickly summarize those key differences again, just to lock it in.
Good idea.
Magnetic field generation. Tokamak uses that internal plasma current plus external coils. Stellarator.
All external, complex 3D coils. No significant plasma current needed for the main field.
Primary confinement. Tokamak combines the toroidal and poloidal fields. Stellarator relies purely on
the coil geometry itself, creating that rotational transform.
operation mode. Tokamak typically pulsed due to that induced current. Stellarator.
Inherently capable of steady state, continuous operation.
Plasma stability. This seems like a big one. Tokamaks are more prone to disruptions.
Yes, those current-driven instabilities can be a real problem. Stellarators are generally inherently more stable because the field is dominated by the external coils.
Confinement? Historically, tokamaks were better here.
Generally, yes. But Stellarators are catching up fast, especially with optimized designs like W7X, aiming to reduce specific loss mechanisms.
And engineering complexity. Tokamak coils are simpler shapes, but you've got the complex solenoid and disruption handling. Stellarator.
Incredibly intricate 3D coil shapes, demanding high manufacturing precision. Different challenges.
Examples. Tokamak ITER, JET, Stellarator Wendelstein 7X LHD in Japan.
That covers the main points, yeah.
Okay, let's dig into that stability point. Why is the Stellarator's inherent stability such a big deal for a power plant?
Well, disruptions in a tokamak aren't just annoying, they can be damaging. When the plasma suddenly loses confinement, Huge amounts of energy and electromagnetic forces can hit the reactor walls.
Ouch. Sounds expensive and causes downtime.
Exactly. You need complex feedback systems to predict and try to mitigate these disruptions, but it's still a major operational challenge. Stellarators being much less prone to these large-scale, current-driven disruptions.
Just operate more smoothly.
That's the potential. More reliable, less stress on the machine components. W7-Tokamaks showing those stable 8-minute discharges is a really positive sign in that direction.
8 minutes of stability sounds way better than trying to constantly fight off instabilities like kinks and tearing modes, or dealing with runaway electrons or ELMs and tokamaks.
It simplifies operation significantly, potentially. That inherent stability is a major draw for the Stellarator concept. Fewer surprises, hopefully.
Okay, now confinement, holding on to the heat. You said tokamaks historically had the edge?
Yeah, they generally showed better energy confinement times, especially if they got hotter. It was a key reason for their dominance.
But Stellarators are improving. You mentioned minimizing neoclassical transport. What is that, basically?
It's a type of energy loss specific to the complex 3D magnetic fields of Stellarators. Think of it like extra little leaks for heat caused by particles drifting in that bumpy field.
Ah, okay.
Modern optimized designs, like the Helios configuration in W7X, are specifically engineered to minimize these neoclassical losses. The goal is to make the Stellarator bottle hold heat just as well as, or even better than, a tokamak bottle.
And W7X results suggest this optimization is working. They're achieving good confinement.
Yes, the experimental results are showing significantly reduced neoclassical transport, pretty much as the codes predicted. They're achieving high plasma temperatures and densities with good energy confinement.
And that quasi-symmetry idea helps here too.
Definitely. By making the magnetic field strength look more uniform to the particles as they spiral along the field lines, even though the field itself is 3D, quasi-symmetry directly attacks those neoclassical losses. It's a very clever way to improve the inherent confinement properties of the Stellarator.
So the confinement gap seems to be closing.
It really does look that way. Stellarators are becoming much more competitive on confined performance.
All right, let's talk steady state again. Continuous power. This feels like the Stellarator's trump card right now.
It's certainly one of its most compelling features for a future power plant. No need for that pulsed inductive current drive means, in principle, you can just turn it on and leave it on.
And W7X pushing for 30-minute pulses, achieving 8 minutes already. That's tangible progress.
It's huge. It demonstrates that the underlying physics and technology can support sustained operation at relevant conditions.
Whereas tokamaks are still working on complex workarounds for continuous operation, right? Non-inductive current drive.
Exactly. Using radio waves or neutral beams or relying on the bootstrap current. It's an active area of research, and they've had success. Taurus Supra in France managed 6.5 minutes.
Still impressive, but it sounds like an add-on, whereas for Stellarators, it's more built in.
That's a good way to put it. The path to steady state seems more direct for Stellarators, which is obviously very attractive for generating electricity reliably.
Okay, back to the engineering nuts and bolts. Those crazy 3D Stellarator coils versus the, well, simpler-looking tokamak coils.
Yeah, the manufacturing challenge for Stellarators is undeniable. W7X required incredible precision, sub-millimeter tolerances over meters of complex curves.
Wow.
But tokamaks have their own beasts to tame. That central solenoid, it's under immense stress, huge magnetic fields, massive currents. Designing and building that reliably is a major challenge.
And the disruption mitigation systems you mentioned, they have to be robust.
Extremely robust. They have to handle enormous forces very quickly if a disruption occurs. So it's not like tokamaks are simple. They have different but equally significant engineering hurdles.
So it's a trade-off in complexity, not just one being easy and one hard.
Exactly. And as we said, the game is changing. Better computers make designing Stellarators easier. Better manufacturing makes building them more feasible.
The playing field is leveling out.
It seems to be.
Yeah.
Historically, the perceived engineering simplicity might have favored tokamaks, but advanced Stellarators are looking increasingly buildable.
Which brings us right back to Wendelstein 7X. The proof is in the plasma, as they say. What are its main scientific goals, boiled down?
Okay, key goals. 1. Demonstrate stable, steady-state capable operation at reactor-relevant conditions. 2. Prove their optimized Helios's magnetic field really works for good confinement and stability, hitting a target beta of 5%.
Beta being a measure of efficiency, right? How much plasma pressure you hold for a given magnetic field strength.
Exactly. 3. Show they've successfully minimized those neoclassical transport losses.
No.
4. Achieve high plasma density. 5, test their novel island diverter for handling heat and particle exhaust.
The island diverter, that sounds different.
It is. It takes advantage of natural magnetic structures, or islands, at the plasma edge in their specific design to channel heat and impurities out. And finally, just understanding how the plasma interacts with the walls in this complex 3D environment.
That's a heck of a to-do list. What about the machine itself? Size? Power?
It's pretty big. Major radius of 5.5 meters, plasma volume about 30 cubic meters. The magnet system is the star. 50 complex non-planar coils, 20 simpler planar ones, all superconducting, hitting up to 3 Tesla.
And heating. How do they get the plasma hot?
Primarily with electron-cyclotron resonance heating. ECRH think powerful microwaves. Initially around 15 megawatts, aiming for 10 milliW steady for the 30-minute goal. They plan to add neutral beam injection, NBI, and ion cyclotron heating, ICRH, later for more power.
And that island diverter handles the exhaust.
Got it. So what are the headline results so far? Has it delivered?
Yeah, significantly. They've confirmed the optimized field gives good confinement, much as predicted. The island diverter works, controlling impurities. They regularly hit high densities and temperatures.
What about fusion performance? They set a Stellarator record for the fusion triple product back in 2018. That's density times temperature times confinement time. Still below the best Tokamaks, but a big step for Stellarators.
And the long pulse.
The 8-minute discharge in 2023 was huge. They turned over 1.3 gigajoules of energy in the plasma-sustained high power. And crucially, analysis shows those neoclassical losses are reduced, validating the design.
So the optimization strategy is working.
It seems to be. The focus now is pushing temperatures higher, increasing the energy throughput, moving closer to reactor conditions. W7X is really making a strong case for optimized Stellarators.
It's great to see that kind of progress. Is this cross-pollinate? Do Tokamak advances help Stellarators and vice versa?
Oh, absolutely. Loads of technology transfer. Heating systems, MBI, radio frequency mostly developed for Tokamaks are crucial for Stellarators.
Diagnostics, too. Measuring the plasma.
Yeah, sophisticated diagnostics, control systems, material science for plasma-facing components, understanding turbulence. A lot of that knowledge base built up in the Tokamak world is directly applicable and beneficial to Stellarators. Diverter tech, too.
Makes sense. Plasma physics is plasma physics. What about the other way? What are Tokamaks learning from W7X and other Stellarators?
Well, the validation of these highly optimized magnetic fields and the success of quasi-symmetry principles is valuable data for everyone. It shows complex optimization can really pay off. Also, demonstrating stable, long-pulse, high-density operation, which is a natural strength of Stellarators, provides important data points and maybe inspiration for Tokamak paths toward steady state.
And the island diverter.
Yeah, understanding how that works in W7X's 3D geometry gives crucial insights for handling the immense challenge of heat and particle exhaust, which is critical for both Tokamaks and Stellarators in a power plant scenario.
What about high-temperature superconductors, HTS? They seem poised to shake things up everywhere.
They really could. HTS magnets promise much stronger fields, potentially allowing for smaller, more compact, maybe cheaper reactors. That applies to both concepts.
But is it harder to use HTS in those complex Stellarator coils?
Potentially, yes. There are unique engineering challenges with HTS tapes. They can be brittle, sensitive to strain, and winding them into those intricate 3D shapes is tricky. It's a big R&D area right now for future Stellarator designs.
Good to remember, too, that while Tokamaks and Stellarators are the main focus, they aren't the only fusion game in town.
Not at all. The field is broader than that. You've got concepts like magnetic mirrors, linear devices, using strong fields at the ends. They're seeing renewed interest thanks to HTS magnets.
Right, the FLAM experiment.
Exactly. Then there are field reverse configurations, FRCs. These are fascinating sort of self-contained plasma toroids, no hole in the middle, potentially very compact.
And inertial confinement fusion, ICF, laser zapping pellets.
Yep. NIF achieving net energy gain was a massive scientific milestone there, though translating that into a power plant is still a long road. Plus other novel ideas, Z-pinches, levitated dipoles, lots of innovation happening.
So the future isn't necessarily just Tokamak versus Stellarator.
It might not be, but the progress of W7X certainly strengthens the Stellarator's position as a very serious contender in the current landscape, regardless of these other emerging concepts.
Okay, let's wrap up this deep dive. Key takeaways. Tokamaks and Stellarators are the leading magnetic fusion approaches. Distinct pros and cons.
Tokamaks have the longer development history, generally good confinement demonstrated historically. Stellarators offer inherent stability and a clearer path to steady-state operation.
And Wendelstein 7X is crucial. It's providing strong evidence that optimized stellarators can overcome past limitations, showing long pulses, high densities, and reduced losses, making them look very viable.
Definitely closing the gap and highlighting their own unique advantages.
But the future? Still uncertain. We can't say for sure which design will win out or if something else emerges. Hybrids are even possible.
Right. Predicting the winner is tough. What's clear is that continued R&D across the board on all these concepts, plus enabling tech like HTS, is absolutely vital if we want to get to practical fusion power.
So here's a final thought for you to chew on. Given what W7X is showing about the potential for continuous, disruption-free power from stellarators, how might that kind of reliable, stable energy source fundamentally change things? Think about our energy grid, our society. What new possibilities might a truly continuous fusion power source unlock, especially compared to, say, intermittent renewables or the potential headaches of pulsed fusion reactors? Something to ponder.